In this lecture video, we're going to continue on by looking at some examples of random experiments, events, sample spaces. We'll look at how to calculate probabilities in certain contexts. We'll look at how to create new events from old events and so forth. So let's start off with a very simple example. The experiment is to flip a coin and record the up phase. Now remember the definition of a random experiment. It's a process or procedure with a well-defined set of outcomes for which we cannot predict the outcome with certainty. And so in this case, that certainly satisfies those conditions. When we're flipping a coin, all right, we have two possibilities. We could get heads or we could get tails. Right? Those are the only two possibilities, and so we have a well-defined set of outcomes. And on any given flip, we're not able to predict with certainty what outcome we're going to have. So this is, in fact, a random experiment. Now the sample space, which again is the collection of all possible outcomes, the set of all elementary events, is the set containing two outcomes, which I'll denote by heads and tails, H and T. All right, so that is a very simple example, perhaps the simplest example possible of a random experiment. For our next example, let's consider the process of flipping two distinguishable coins, say a quarter and a nickel, and then recording the up faces. Now that is a process that has a well-defined set of outcomes. The sample space, which is that set of all possible outcomes, has four elements. All right, so each elementary event, we can think of this as an ordered pair, all right, an ordered pair of outcomes. And let me denote the outcome of the quarter with the first item in the ordered pair, and then the outcome of the nickel as the second. So we could flip the two coins and get heads for the quarter and heads for the nickel, or we could get heads for the quarter, tails for the nickel, tails for the quarter, and heads for the nickel. And then finally the outcome where we get tails for the quarter and tails for the nickel. So there are only four possible outcomes for this experiment. It's a well-defined set of outcomes. On any given trial of the experiment, we're not able to predict with certainty what's going to happen on that trial, but we do know what the outcomes are. So this does satisfy the definition of a random experiment. All right. Now we can define some events of interest here. And events of interest are collections of elementary events. We can also think of composite events as subsets of the sample space. Now one event of interest might be described in words as getting at least one head when we flip these two when we flip these two distinguishable coins. And if we represent that event as a collection of elementary events, or equivalently as a subset of the sample space, then we would have these three elementary events. We could get heads on the quarter and heads with the nickel. We could get heads with a quarter and tails with a nickel, or tails with a quarter and heads with a nickel. In all three cases, we have at least one head. We have two heads here, we have one head here, and we have one head here. So that's how we would represent this composite event as a subset of the sample space. All right. Again, we can also represent the event or describe the event in words. And we can also denote the event using just a letter, as we've done here. And let me just stop here and say that this is a very common convention used in probability, all right, to use uppercase letters near the beginning of the alphabet to represent events of interest, composite events. Okay, the next event that we're talking about here is the event where we flip the two coins and we get no heads. Now, expressed as a collection of elementary events or as a subset of the sample space, that event is the set that contains the one elementary event, tails, tails. So in that case, we've gotten no heads, and there is no other possible outcome where we would have no heads. All right, and let's denote that event by B. And then another event of interest would be that both coins show heads. So we get heads with the quarter and heads with the nickel, represented as a collection of elementary events or as a subset of the sample space. Okay, we would represent it this way. And we will abbreviate this event and denote it by capital C. All right, for the next example, let's think about rolling a die and recording the up face. So a regular six-sided die. The six possible outcomes are 1, 2, 3, 4, 5, and 6, obviously. And so this is the sample space for this experiment. It is a random experiment, right? It's a process that leads to a well-defined set of outcomes. And on a given trial, we're not able to predict with certainty which outcome is going to happen. Now again, we can define some composite events of interest. We could think about rolling an even number, so that would correspond to rolling either a 2, 4, or 6. Let's denote that by event A. We can think about rolling an odd number, all right, so that would correspond to rolling either a 1, 3, or 5. We'll denote that by event B. We can think about rolling a number strictly less than 4, and so that would correspond to rolling either a 1, a 2, or a 3. And finally, we could think about rolling a number that is no more than 4. In other words, a number less than or equal to 4, and so that would correspond to rolling either a 1, 2, 3, or 4. And we'll call this event D. Now let's think about rolling two distinguishable dice and recording the two up faces. And so they are distinguishable. So, if we were in class, I would have my props with me. I've got two large dice that I show. And imagine me standing in front of class holding them up. One of them is a green die and the other is a red die. All right, so those two dice are in fact distinguishable. And we can think about rolling those dice and observing the number on the up face when they stop rolling. We can, an elementary event is therefore an ordered pair of numbers. We'll let the first coordinate of that ordered pair be the number that we get on die 1. Let's call that the green die. And then the second coordinate, the second component of that ordered pair is the number that we get on die number 2, which is the red die. Now there are 6 possibilities for each of the two dice. All right, and so there are 36 possible outcomes for this experiment. All right, and so the sample space consists of these 36 elementary events, each elementary event being an ordered pair. Now some events of interest. One event of interest is that the sum of the two dice is 7. All right, and so expressed as a subset of the sample space, that composite event consists of the elementary events listed here. We could get a 1 with the green die and a 6 with the red die. That would give us a sum of 7. We could roll a 2 with the green die and a 5 with the red die. That again would give us a 7. And again, each of these gives us a sum of 7. Now we're going to denote that event by A. Another event of interest is that die 1 is 3. All right? And so expressed as a set of elementary events, that event consists of the elementary events 3 and 1. So the green die is a 3, the red die is a 1. The green die is a 3, the red die is a 2, and so forth. So you see that in each of these elementary outcomes, the green die, die 1, is a 3. And then the value on die 2 ranges from 1 through 6. And finally, we could think about the event that the larger of the two dice is no more than 4. In other words, the larger of the two dice is less than or equal to 4. And so that composite event consists of these. This is not highlighting very well, is it? But you can see here, we've got these 16 elementary events, all right, that each result in the larger of the two dice being no more than 4. So this composite event consists of 16 elementary events. Okay, let's think about the experiment where we roll 2 indistinguishable dice and again record the up faces. So again, imagine me standing in front of class and I've got 2 dice, but now they're both green. I've got 2 green dice, and so they are indistinguishable. And so when we roll them, we don't know which is die 1 and which is die 2, so we really can't put it in the framework of the previous example. But we can think about what is the larger of the 2 dice and what is the smaller of the 2 dice. And so an elementary event for this experiment is again going to be an ordered pair where the first value, the first component of that ordered pair is the least number, and the second coordinate or the second component of that ordered pair is the greatest number. Now keep in mind that the least number and the greatest number could be the same. For example, you could get a 2 and a 2, and so the least number would be 2, the greatest number showing would be 2 as well. So stating it this way does not mean that the least number has to be strictly less than the greatest number. And so the sample space consists of these ordered pairs here. Now I see here that in these elementary events I've listed, or I've got them listed using brackets. Technically those should be parentheses to indicate, because that's typically how we would represent ordered pairs. So I'll let you make that correction in the notes. Now I want you to notice something. In this experiment, the sample space only has 21 elementary events. In the previous example, where the dice were distinguishable, the sample space contained 36 events. So whether or not, in these problems like this, where we're rolling dice or something like that, it depends on whether the objects are distinguishable or indistinguishable. That has an impact on the number of elementary events in the sample space. And we're also going to see that it has an impact on the probability structure on that sample space. Okay, here's an example that is more real world and less tied to games of chance or the tools of games of chance. So suppose that we are going to select a family with 2 children and record the genders of the 2 children. So this is, we can think of this in the context of a sample survey where we are looking at a certain subpopulation within the more general larger population. In particular, we're looking at the population of families that have 2 children. So we're sampling from that subpopulation. And so an elementary event for this experiment would be an ordered pair consisting of the ages of the genders of the 2 children. So we can think of the first coordinate being the gender of the younger child, and the second coordinate being the gender of the older child. So notice here that when we're talking about ordered pairs, we're not necessarily talking about ordered pairs of numbers. We can have ordered pairs of symbols, as we've got here. And even when we looked at the example of when we were tossing two coins, 2 distinguishable coins, we were using ordered pairs of symbols in that example as well. So again, there are 4 possible examples listed here. And some events of interest might be, for example, that the couple has at least 1 boy. Okay, and so that consists of these 3 elementary events. We can think of the composite event of having 2 girls. Okay, there's only 1 elementary event that satisfies that description. All right, and so and listed or represented as a subset of the sample space. Okay, it would contain this single elementary event.